This video is about the stereochemistry of the E2 reaction. The E2 reaction, again, is going to be a concerted reaction where all three of the arrows that we draw, the proton transfer, the pi bond formation, and the leaving group leaving, all occur simultaneously. This is also going to be a stereo-specific reaction. We'll talk more about regiochemistry as to where the pi bond will form in another video. But for now, we're just going to focus on the stereochemistry. And what I've drawn here is a substrate that is only going to give us one stereoisomer. So that's what we mean by stereospecific. We're going to get a single stereoisomer product. And we'll talk about how to set that up so that you get the correct stereoisomer for the E2 mechanism. And this rule really only applies to the E2 because it is a concerted reaction. We'll talk more about the E1 stereochemistry in another video. But what is going to happen here when we think about the mechanism of the E2 reaction? We have our leaving group, we have our proton, and then we have whatever else is bound to the future vinylic carbon atoms. So in this instance, of course, the alpha carbon is here and the beta carbon is here, and we only have the one choice. And that beta carbon in this particular example has 3 protons on it. So we could choose any of these 3. But there's a reason I set this up like that with the H and the leaving group. And this is the H that I'm going to take. Notice that these are anti-periplanar. If you want to simplify that, you could just say that they are anti to one another, meaning that they're going to have a 180-degree dihedral angle. So if we were to draw the Newman projection for this, and let's say that we're looking at it from this perspective with the leaving group in the front, we would have the 2 hydrogen atoms here and here, another hydrogen atom there. And so the hydrogen atom and the leaving group that we're talking about of interest are like this. This is going to be anti to one another. And this is the setup we have to have. And the reason for this is explained in the Carty book on page 368 in Interchapter C. And what it shows is how the orbitals go from the sp3 hybridized compound to the pi bonds that we're going to end up with. So what we have here is that with the leaving group, there's going to be the lowest unoccupied molecular orbital. So this is going to be the LUMO, or the first sigma star orbital for the carbon with the leaving group, the alpha carbon. And then the HOMO, the highest occupied molecular orbital, which is going to be what the CH bond is going to look like this. So this is the HOMO for this particular carbon atom, or for this particular setup, and this would be a bonding interaction. But you can see here how even though these are sp3 hybridized, both of these, they kind of look like they're lined up so that all they have to do is sort of shift to the right. So as the reaction happens, again, this is all concerted, the base will grab the proton, the pi bond forms, and the leaving group leaves. This is going to rehybridize into sp2. We're going to end up with the pi bond like this. Okay, so you can see how the HOMO of the beta carbon and the LUMO of the alpha carbon sort of can shift readily into that setup. For the syn configuration, if they were lined up either 0-degree dihedral angle and eclipsed, or if they were in any other situation, the orbitals would not be lined up in a nice way in order to form the pi bond. So this is why whenever you're doing E2, if there is, so the only time you need to worry about this is when you have a setup like this one. So for this particular one, I'm just going to tell you that this is the beta carbon where we're taking the hydrogen atom. So there's only one hydrogen atom on this beta carbon here. And so this is the one, sorry, I'm going to change the structure here just a little bit. This is the one that we're going to take that proton. And then here's the leaving group. So what we have to do is we have to redraw this to set this up to be anti-periplanar. The other thing I want to do here is just kind of show the transition state before we go through and draw the mechanism out. Excuse me, draw out showing how to do the stereochemistry. So the transition state for this one, when you have the base, going to grab that proton, pi bond forming, the leaving group leaving. So that transition state is going to look like this, where the base H bond will be forming, the H carbon bond will be breaking, the pi bond will be being made, and the leaving group will be leaving. So all of that is going to be happening simultaneously. And when that happens, what's going to happen is that we're going to have a positive charge buildup here at the alpha carbon, okay? And so we'll talk more about that later when we talk about the regiochemistry of the reaction, or actually what favors the reaction. But that's what that transition state's going to look like. Okay, I need to make a little space here to actually draw out the reaction. So I'm going to erase some of this stuff here. Okay, so the first thing I need to do is I need to rotate this structure so that I do have the H and the leaving group anti to one another. So I need these to be anti. And for me personally, the simplest way to do this is to put the H in the plane, probably up in this instance, and the mesylate leaving group in the plane down. So I'm just going to rotate each of those carbon atoms. So if I have the hydrogen atom in the plane, that means this methyl group here is going to rotate forward and down. And then this ethyl group, and I'm just going to abbreviate these to make it easier on myself for a little bit, and then I'll convert it back to the actual bond line drawings. This ethyl group is going to rotate to the back, but still be down. On the right side, that mesylate, I'm going to shift forward. First, I'm going to go ahead, though, and draw on my hydrogen atom, just to help me remember that I have that. So OMS. So I'm going to rotate the OMS towards me, which is going to shift the hydrogen atom up, and then the methyl group over here will be up and back. So this is, of course, a perfect place to use your model kit if you would like. And as always, you can bring your model kit to any quiz or test or exam, including the final exam. You can bring a pre-built ethane with 3 different groups, including one of them being a hydrogen, on one carbon, and 3 different groups, whatever you want them to be, on the right side. And then, when you're doing this, you can do that rotation so that you can see it a little bit easier. But you may not need that, and that's fine. Obviously, doing it on paper, well, I think either way could be pretty quick. So whatever gets you there consistently is the way you want to go with this. All right, so now we have our hydrogen and our leaving group are anti to one another. So now we have the setup that we need to actually carry out this reaction. One thing I didn't say here was what the base was. So for this particular one, I'm going to use an AOCH3, which that's going to be sodium methoxide. And whenever we see sodium, of course, we're going to remember that that's going to be a spectator cation. And then this will be the methoxide, excuse me. So that's going to be our base that's present. So I'm going to draw this over here. Okay, so now we have everything set up for that LUMO on the alpha carbon and the HOMO on the beta carbon to just shift over and make that new pi bond. The thing I want to point out here is that the methyl and the hydrogen are both on wedges. And so when we draw our pi bond, the methyl on the left carbon and the hydrogen on the right carbon are going to be pointing the same direction. And then the ethyl and the methyl are both on hashed wedges. So those are also going to be pointing, these are also going to be pointing the same direction. When we draw a pi bond, we typically don't, unless there's some particular reason to draw it kind of rotated and coming in and out of the plane. We don't draw wedges and dashes because this is going to be trigonal planar. And so for that reason, we can draw it flat into the plane of the paper. So over here, the methyl and the ethyl are pointing the same direction. Okay, and so I'm going to redraw that in the bond line structure. Okay, and this particular one, we could name it if we wanted to or needed to. We would start over here, 1, 2, 3, 4, 5, because that gives us the longest parent chain. And here, the highest ranked group we have is the alkene, and we want to give it the lowest locant possible. We have that methyl group at the 3 position, so that'll be 3-methyl, hex 2-ene. Now, we do have, this is something that we can label as sister trans or E or Z. Technically, we could call this trans because we have the 2 methyl groups, but let's go ahead and just refresh our memory on how to assign E or Z. Remember, we're going to look at each vinylic carbon atom, and the vinylic carbon atoms are the double bonded carbon atoms. And we're going to compare the atoms immediately attached to each of those. So we've got carbon and hydrogen. So carbon, of course, is going to be the higher ranked of these two. And then when we look at the other carbon atom, or the other vinylic carbon atom, we see we have a carbon and a carbon. So that's a tie. So we have to go out to the next set of atoms to compare those. The one on the bottom has 3 H atoms. The one on the top has a carbon and a hydrogen, So because of that carbon atom, that's going to mean this is going to be the higher ranked one. And these are on the same side, so this is going to be Z. So it'll be Z 3-methyl hex 2-ene. And because this is a stereospecific reaction, the other stereoisomer, which would be this one, we're not going to get this one at all because that one would not come from having the proper anti-periplanar setup of the hydrogen in the leaving group. So we're not going to draw that reaction product at all as a possibility. So when you're doing E2, and really again, you only need to worry about this if the beta carbon that you're coming from has a single hydrogen atom. If that beta carbon has 2 hydrogen atoms, then you're going to be able to have that anti-periplanar set up with both of those hydrogen atoms, which means you're going to be able to get both stereoisomers if it is indeed stereoisomeric. And so then you would choose the most stable one, which we'll talk about in another video. So look for the alkene stability video as well.